In this video, we're going to generalize the idea of the left-hand sum and the right-hand sum to a range of expressions that are called Riemann sums. They're named after Bernhard Riemann. The idea behind these is not complicated. What we've seen before was we took heights and we took widths and we multiplied them to get the area of a rectangle, and we did that many times over a series of intervals to get a final sum. The only generalization we're going to add here is recognizing that a left-hand sum, imagining a graph like this, going to the left-hand end and then going across and building a rectangle is one way to do the construction we're talking about. Going to the right-hand endpoint and using that as the height is another, but there's no reason why the left hand or right hand is particularly special. We could pick any point in the middle, and that's what this little star notation here is typically used to represent. The star just means some point on that interval, and using that to build the rectangle. Whatever we use to build the height, it's always still going to be a height times a width added up over all the intervals that we need to cover the span from A to B. Anytime you feel like there's this combination of a height times a width for an area, or possibly a velocity times time to get a distance, and you're adding that up over small intervals, that in shorthand is what we mean by a Riemann sum. To formalize that a bit, all of these approximations have in common that they're sum of rectangular areas, there's a width, and there's a height evaluated by putting an x-coordinate on an interval into our function. There are ways to improve how this calculation works by being a little more sophisticated, but that's something that we'll see a bit later. For now, the most important idea is just that we have this width times height construction, and that we can do that to compute rectangular areas that approximate a curved area. Where is this leading us? If we have all these sums, and they're always estimates, well, there's a natural intuition that says if we had a graph, and we estimated the area under that graph with rectangles this big, it's a bit crude. Take the same graph and use smaller intervals, it gets more accurate. Use smaller intervals still, and again, think of resolution on a monitor. If you want an example of this, the more pixels or the smaller the pixels are, the more closely we can match the shape of the graph, and so the more closely we can match the area under the graph. Imagine using lots and lots and lots of rectangles like this. This would be a very, very high accuracy approximation. And so here comes the inspiration. If we have our Riemann sum, here would be the left sum. If we want to get the exact area, one way to get there is to simply use more and more rectangles. What's our tool in calculus for doing that? It's by saying we want the number of intervals, or the number of rectangles, which is n, to approach infinity. Another way to say that is the delta x's, which is the width of each rectangle, is going to 0, while still covering the entire range from A to B. Each subinterval that we use is getting smaller and smaller because we're using more and more of them. So this is where we connect our relatively crude approximations we've done earlier and use the limiting technology we have from earlier in the course to get an exact value for the area under a graph. So when we talk about that exact area, we're going to have a new name for that. It's going to be the definite integral of the function, and we have to specify where we start and where we end, and that's going to give us the area under the curve, with some caveats here about it being non-negative and continuous. We'll dive into that in a little bit. But the key thing is, intuitively, with a graph, if someone says, I'd like you to look on this interval from A to B, and here's your function, the exact area underneath this graph, the area highlighted here in red, that area is equal to this notation here. Here's my function, there's a little dx, we'll see why that's there, and then there's the A to B. Integrate from A to B my function with this dx here. Other nomenclature, the A and the B, here and here, are called the limits of integration. They're where you start and stop calculating the area, so limits in that sense. The f of x part is called the integrand. The whole thing's an integral. This is the integrand, is what's inside of the symbols here in the middle. And for now, the dx is something that just denotes the variable we are using. So these guys have to match essentially for now. One of the rationales for this particular set of symbols is that it ties into the Riemann sums that we saw before, where the function is the function. What was a delta x before is now a dx, and that matches what we saw in the derivative side. When we let delta x get smaller and smaller and smaller, we'd call it a dx and a derivative. And instead of the summation notation here, we use this curved s, which is the integral, but it represents a sum again. So you can think of adding up the function f of x times delta x's from a to b, but with the delta x being a very, very tiny amount, or in the limit, an infinitesimally wide rectangle. What this notation allows us to do is very quickly write down what we mean by the area underneath a graph. So imagine we've got a graph defined by f of x as x plus cos of x. I'm not sure quite what that looks like, but oscillations plus going up. And we want to capture that between x equals 2 and 4. Fair enough, that's a certain area underneath a graph. That area is going to be equal to the integral of the function, so x plus cos of x, put brackets around this whole thing, with respect to x, and we want to start at 2 and end at 4. So we can very easily write down notationally what we mean by this exact area. Now, we can't do much with this immediately, but that's where we're going to be heading, is how to handle this with some sophistication as we move forward.